A theory is not a fact. If it were a fact, we would call it a fact. If it's not a fact, we call it a theory. Now, a theory is a supposition. It is a hypothesis. It is a theist. It is a conjecture. It is a postulation. It is a thought that hasn't become true yet. It might be true, but it also might not be true. And that's why we call it a theory. The word comes from spectator, to speculate. That's it.
You have to understand what it means for something to be a theory. There's a lot of misunderstanding about that. If you have a new idea and you want to test it, that's a hypothesis. If there's countless objects and phenomenon out there that have conduct or behavior that can be brought under one umbrella of understanding, and that umbrella of understanding allows you to make predictions that are then shown to be true, then you have a theory.
Just call a theory a fact? Did you just do that? Did you just call a theory a fact? You're very good at explaining the theory of global Earth theory. You're very good at that. You're very good at that. I applaud you for that. I applaud you for that. But it is just a theory, and it is not proven. You have no proof of motion. You just don't. You just don't have proof of motion. It's a theory. And theories are not facts.
Let's look at the planetary rotation. Does that
Does
not engage with a field kick?
So if you have a north-south stadium, and many are, if it's oriented that way, and the kicker kicks the ball, depending on how high and how long it's in the air, the rotation of the Earth can have a significant effect on its trajectory towards the goalpost. If you're trying to make a 50-yard field goal, that's far away enough, and the ball is airborne long enough for the rotation of the Earth to deflect it to the right by 1/3 of an inch. Cincinnati Bengals against, I forgot who, was it Seattle Seahawks? In overtime, sudden death kick went up, and everybody's heart stops and no one breathes, and there it tumbles, and it hit the left upright and went in for the win, but kind of barely went in. And then I tweeted, I said, this game was won assisted by the rotation of the Earth. And that force that makes that happen is the same force that sends hurricanes rotating counterclockwise in the northern hemisphere and clockwise in the southern. What's his name? Felix Baumgartner. He would have been about 2 millimeters above the surface of this globe. That's his edge of space jump. Now, you know, I don't, it's fine. He wants to, I don't have a problem if he does it, but the honesty of it would greatly diminish what I think people thought he was actually doing. And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines. Right. So in the photo, you see this curvature of Earth's surface, and he said, wow, he's in space, look at that. No, he's not. At that height, you don't see the curvature of the Earth if you are 2 millimeters above this beach ball. You just don't. That stuff is flat. And then I showed examples of wide-angle lenses curving horizontal. I tweeted that.
What is gravity?
You have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
So did I accidentally ask a deeper question than I meant to?
Yeah, no, you were meant to ask deep questions.
Apparently I was.
In life. So to say, what is it? I think Einstein, in an Einsteinian answer, we would say gravity is the curvature of space and time. And objects will follow the curvature of space-time, and we interpret that as a force of gravity. That's probably the best answer I can give to a what is gravity question, or why is there gravity. That's the best I can do there. I think that's a good start. And I can also say that Einstein noted that matter tells space how to curve. Space tells matter how to move.
Say that again.
Isn't that beautiful?
It is. No, I want to get that. I like that. That's a t-shirt.
Matter and energy will curve the fabric of space.
Okay.
And it's that curvature that tells other matter how to move in the curvature of space itself. And so Einstein juxtaposed those in a poetic phrase where he said, matter tells space how to curve, space tell, did I get that right? Yes. Matter,
I wouldn't
matter
know.
tells space how to curve, space tells matter how to move. And this is after Newton's laws of gravity are published. So now we're tracking the orbit of Uranus. You see, no, this is not following Newton's laws. It's got some deviation. So maybe we found the limits, the distance limit over which Newton's laws would apply. That'd be interesting. But other people said that Newton was so badass, it must work, okay, even there. So instead of suggesting that his law was failing, clever people said maybe his law applies. But there's yet another planet out there that we've yet to discover whose gravity is tugging on it, and we did not include that in our calculations. So let's do the math and ask, where must there be a planet of what mass to create the deviation that we measure? And those calculations were done, and they were published. And an observatory in Germany got hold of those calculations. And they looked in the exact spot of the sky that the calculation said Neptune was waiting to be discovered right there. It was a triumph of Newton's laws. And so this gives us confidence. We're not just pulling this out. We calculate this, and the observations show it. So now watch what happens. We have better and better measurements, and we find out Newton's law is failing. Mercury's orbit is not following what it should. That's the closest planet to the sun. Well, we've been down that path before. Just throw in another planet that we can't see, and that'll fix it. So, thus was introduced planet Vulcan. This would be a planet very close to the sun, so close it would be hard to see, it would be lost in the glare. And so there was the hunt for Vulcan. No one found it. But we knew it had to be there, because that's the same problem as the discovery of Neptune. Einstein comes along, comes up with his theory of motion and his theory of gravity, the special and general theory of relativity. Out of those two theories, which are corrections to Newton's laws in these extreme regimes. If you're near the sun has very strong gravity. If you're moving around in that strong force of gravity, Newton's laws begin to fail. And no one knew this. And you look at Einstein's laws, and he says, Mercury's orbit will not follow Newton's laws, it'll follow this other path. Find out. And it exactly explained the deviations of Mercury. And so people say, oh, see, scientists, we thought this was right, and now we all huddle around this thing that's right. No, that is not how it works since 1600 onward. The way it works is if you have an experimentally determined result, and it's verified and double-checked and triple-checked, that will not later be shown to be false. What you can find is a deeper understanding of the world that encloses that understanding. And that's what happened with Einstein. Einstein's theories of motion and gravity, if you put in low speeds and low gravity in the equations, they become Newton's equations. So Newton's universe is a subset, an accurately described subset of a larger universe that Einstein has described. And even with Einstein, his equations can't take us to the center of a black hole, the singularity that's there, the singularity at the beginning of the universe. We know now that his theories fail. They blow up on the page. So we have a whole frontier of science. The string theorists, you've heard of them. The string theorists, we got top people working on this to try to extend Einstein's laws into an even bigger regime that can then explain everything that's in our universe, not most things. So it turns out there's no such thing as centrifugal force. It's the word we give to this thing that feels like a force operating on you if you are the water in that bucket, or if you're in that amusement park where I think they call it the cyclone, where you're sort of pinned against the wall of it and it rotates and you feel this pressure increase on you. So what's happening is, because you're getting spun, you have an urge to fly off at a tangent of that circle, okay? That urge to fly off that is prevented, you will feel as a centrifugal force. Okay. So if you divide those two numbers, you get they're going to approximately 1,000 miles an hour.
Right.
Okay? Right. And that's fast. I mean, that's faster than you would ever be going in anything in your life.
That's right.
Okay? Now, you don't feel that because first, Earth connects you to its surface, but also you're moving very uniformly through space to do so. And the air around you is moving with you. So it's not like air is coming past you at 1,000 miles an hour and you feel, oh my gosh, I'm in motion and I feel the jiggle and the shake. By the way, pre-Galileo, people's arguments against Earth's motion was if Earth were turning and moving, we'd feel it.
Right.
Okay? Why wouldn't you feel? If you're on a horse and buggy, you feel that.
Feel it.
All right? You feel the bumps and the wiggles and the jiggles, and even if the ride is smooth, you feel it. So clearly Earth can't be moving. Of course, we're not rotating either. Everything is moving around us. So it wasn't just our ego that supported the idea that we are in the center of all things. At the center of all things. It's not just what's happening with our ego. It kind of made sense when you thought about it. Okay?
Right.
What they didn't realize is that if you made things smoother and smoother and smoother, you will feel the motion less and less and less. Hi, I'm Neil Degrasse Tyson, your personal astrophysicist, and I'm here at Penguin, UK, to answer some of your deepest, most pressing questions. Typically 2 people, and there's an audience, and you debate some opposite sides of some issue, and then there's a winner of the debate. And then everyone walks away reflecting on the winner. So who wins a debate? It's often the person who's charismatic, who's maybe charming, that's related to charisma, of course, who has a good way with words, good vocabulary. And you can have someone who doesn't have any of that, who is speaking objective truths, who could lose a debate. So then what is the point of the debate if one of these points of view is objectively true? I got your distress call. Is everything okay?
No, Neil, everything is not okay. This BS about the Earth being flat is getting out of control. Can you please help us?
All right, hold my sandwich.
Oh, sure.
Okay, I'm sorry.
Here, you take that. Here. You want to?
Oh. All right, listen, B.O.B., once and for all. The Earth looks flat because, 1, you're not far enough away at your size. 2, your size isn't large enough relative to Earth to notice any curvature at all. It's a fundamental fact of calculus and non-Euclidean geometry. Small sections of large curved surfaces will always look flat to little creatures that crawl upon it. But this whole thing, it's just a symptom of a larger problem. There's a growing anti-intellectual strain in this country. It may be the beginning of the end of our informed democracy. Of course, in a free society, you can and should think whatever you want. And if you want to think the world is flat, go right ahead. But if you think the world is flat and you have influence over others, as would successful rappers or even presidential candidates, then being wrong becomes being harmful to the health, the wealth, and the security of our citizenry. Discovery and exploration got us out of the caves, and each generation benefits from what previous generations have learned. Isaac Newton, my man, said, if I have seen farther than others, it's by standing on the shoulders of giants. Can I get an amen? Woo. So that's right, B.O.B. When you stand on the shoulders of those who came before, you might just see far enough to realize the Earth isn't flat. And this is called gravity.
Is gravity.
You have no idea. Okay, next question. And I would say it's not about whether they've had education. It's about whether the education they had teaches them skepticism of information and teaches them how to inquire. Do you realize it's just as intellectually lazy to believe everything you see as it is to deny everything you see?
Yes.
Why should someone know automatically that Earth isn't flat? Yet I tell them in the next breath that the entire universe was once as small as a marble. Right? Both of those sound equally preposterous, except one has evidence to back it and the other does not, and very strong scientific, theoretical, and experimental underpinnings. Football tweet.
What other
about
football
was it
tweet?
the Bengals? I forgot who it was, about a year ago.
Yeah.
There's in overtime, after there was the exchange of balls, so now it's sudden death overtime. They kick a field goal from 50 yards, of course, as it must be, and 40 yards out plus the 10 plus the hiking distance. So it was like 52-yard field goal, and there it was. And if there's tense, right? Everybody's silent, and the ball comes up, and it careens off the left upright and goes in for the win.
Wow.
And I said,
I remember this.
That's what I'm saying.
I remember this
That's
tweet.
what I'm saying. So I'm there and I said, wait, the angle of this, how long is it? So I checked the stadium on its configuration, what's longitude and latitude, and I said, I did a quick calculation, and I tweeted, the winning field goal in that game was aided by a 1/3 of an inch deflection to the right from Earth's rotation. Fractions of an inch matter. A handful of experiments in physics that completely transformed physics. At many people's top of the list would have to be the Michelson-Morley experiment.
In the 19th century, physicists thought that since sound waves travel through air, light waves must travel through some sort of medium as well. They called this theoretical medium ether.
The famous luminiferous ether. This magical medium that was hypothesized to be what light required to move through the vacuum of space, just the way sound requires air to move from one place to another. How else could waves of light move through the vacuum of space unless there was some medium there, some hypothetical medium? Let's call it the ether.
Ether, they theorized, is an invisible nothingness that permeates the universe. The physical property is that it allows light to propagate through it. But once precise measurements of the speed of light became possible, testing the predicted effects of ether on the speed of light became possible as well. The Earth orbits the Sun at about 66,500 miles per hour. If light travels through ether, they reasoned, then as the Earth moves through the ether, the speed of light should be different going with the ether than perpendicular to it. In an attempt to show the effects of ether on the speed of light, Albert Michelson and Edward Morley conducted an experiment in 1887 at what is now Case Western Reserve University.
Michelson was an expert in optical experiments, and he thought that he could devise an experiment where one would be able to see the slight difference in the speed of light measured on the Earth if you measured it along the direction of the motion of the Earth and at right angles to it. There should be a slight difference.
Compared to the speed of light, Earth is not moving that fast. So if you're going to check the difference in the speed of light, measured with the movement of the Earth compared with transverse to it, you need a level of precision that no one had before. The Michelson interferometer was just such an apparatus.
Michelson and Morley devised an apparatus that would detect minute differences in speed between two beams of light. Light from one source is split into two directions through a half-silvered mirror. These beams are bounced between other mirrors and then recombined back into a single beam. When two light beams combine, if their waves are completely synchronized, the peaks combine to make an even more intense peak. If they are one half wavelength off, their peaks combine and cancel out the intensity. Slight differences in speed between two light waves will therefore produce a pattern based on the amount of interference between the two beams. This is known as an interference pattern. Examining the interference pattern from the two light beams sent out in different directions would clearly show if the speed of each light beam were different in different directions. But Michelson and Morley never detected such a difference. Their results were inconsistent with the existence of ether.
The scientific world didn't know what to make of it. The famous scientists in Europe, all Lord Rayleigh and Lord Kelvin and Lord Thomson, were saying, hey, come on, you must have done something wrong here. There has to be an ether. And the whole thing didn't get resolved until many, many years later when Einstein came along.
Einstein's theory of special relativity proposed that the speed of light is always the same, regardless of the speed of the light source. The results of the Michelson-Morley experiment were entirely consistent with Einstein's view of the universe, and this served as the turning point in modern physics.
The Michelson-Morley experiment was an experimental advance in technology that transformed science. Not only physics, but science.
No, what it did, Neil, is prove that the Earth isn't spinning. There's two causes of the light, and yet there's only one cause of the light shown in the experiment. You know this, and you know this is what led to Einstein's general theory of relativity. And this is just an assumption by Einstein that the Earth is moving. He just assumes the Earth is moving. He assumes that mass and light speed are the same thing. Energy equals that. What's the cause of the energy? The Earth's rotation is just an assumption, and you know that. It's called a theory.